All right, so today we are starting to talk about linked lists. So the deal is that up until this point, we basically have one way of storing a lot of data in a variable, right? Basically, we use an array. That's pretty much it. We did talk about vectors a little bit, but really a vector, if you look behind the scenes, a vector is just an array anyway, right? So in terms of how efficient things are going to run and those sorts of things, really arrays is our only option. What we're talking about with linked lists is we are going to study something completely new, a new way of storing large amounts of data. The STL class that we're going to be basically imitating here or simulating is the forward list class. And so in one sense, what we're doing here is it'll give you an idea of what's the difference between a vector and a forward list, the STL vector and the STL forward list when it comes to how things are working behind the scenes. So basically what's going to happen with a linked list is that instead of having all of our data stored in a contiguous area of memory, we're going to use the heap, and we're going to have each piece of data is going to be stored just in some random location on the heap, but it's going to be associated with a pointer that points to the next piece of data in the list. So the way that we connect the different data and have a way of keeping track of it is that we just have pointers from one piece of data to the next. So to show you a picture of that, here's a picture of a linked list named list. It's a local variable on the stack. This thing here is a struct or a class, either way. I'm going to call it a struct for our purposes. And so it's got two data members, one that we're calling data that stores the piece of data that we're storing, and then another data member called next that points to the next node in the linked list. So this is a picture of a linked list that is storing the numbers 47, 19, and 62. We have to have some way of indicating when we have reached the end of the list. So what we do is we make the next pointer of the last item in the list equal to null pointer. And so that's just our sort of our signal that we have reached the end of the list. So in one sense, that's really all there is to it. And, I could say, okay, we're done. Now you go, write some code to implement this data structure that I've described. I won't do that to you. We'll actually go do some code. But from now on, basically all we're doing is we're just writing code to implement what I just described. Anybody want to ask a question about how any of this works before we keep going? Okay. So let me just digress for a second and let's talk about why on earth we would ever want to do something like this. So first, let's talk about the downside of using a linked list instead of an array. Let's say that we are trying to store 1 million items, okay? If we want to access the 1 millionth item in an array, how many steps does that take? Anybody want to take a shot at that? I'll give you a hint. It's an easy question. You could all do that, right? If I said, okay, declare an array with 1 million items in it and then access the last item in the array, right, exactly. Index sub 9999999 would give us the, would access the last item in the array. So one step. With a linked list, it would take 1 million steps, because there's no way to get directly to the last item in the linked list. You just have to start at the beginning and work your way down until you get to the 1 millionth item in the linked list. So that's really bad, right? In fact, we talk about this in terms of efficiency. We're going to say that access in an array is a constant function, right? It just takes one step, doesn't matter how big the array is, right? Linked list linear, right? So in other words, if you were to write a function stating how many steps it's going to take to access an item in a linked list, that function would depend on the number of items in the list, right? And you know, just very briefly speaking, we could actually say that if there are if we're trying to access the nth item in the list, then it's going to, the amount of time it's going to take is n steps, or the number of steps it's going to take is n. Okay, so don't worry too much about that math. I'm just sort of giving you a sneak preview of the stuff that you'll be talking a lot about when you get to your data structures class. Okay, so that's the downside to a linked list. Another downside to a linked list is that we'll be using a little more memory, because along with each piece of data, we'll also be storing a pointer, right? However, that's rarely important, right? It's much more important. This is a much bigger distinction, right? The difference between being able to access something in one step versus being able to access it not in one step. So a little more data, a little more memory is being used because we're storing all these pointers. All right, how about an upside? So imagine that we have an array with 1 million items in it, and we need to insert something at the front of the array. What are we going to have to do? Use pushback or something similar. Right. But if it's an array, we don't have pushback, right? And pushback would be putting something at the end of the array anyway. I'm asking about putting something, inserting something into the beginning of the array. And whether or not we, yeah, right, array sub 0, except, okay, some good answers here. Okay, so a use array sub 0, that's correct, but we can't just put the new item into array 0, because then we'll be erasing what used to be the first item in the array, right? So the point here is that if we want to insert something at the beginning of an array, we have to shift every item in the array down by 1 to make room for the new item that we are inserting there. Does that make sense? I see a couple other responses here that I'm going to get to in a minute. But I guess the most fundamental piece is that we have to shift everything down. Anybody want to say that doesn't make sense? I mean, I could draw a picture, but I'm hoping that makes sense. So what that means is that array insert is linear, right? It depends on how many items there are in the array, because we're going to have to shift every item in the array down one. Linked list insert. If we want to insert something at the beginning of a linked list, we just create another node. And I'll be talking about this in more detail in a minute. Create another node and then make this pointer point down here, and then make this guy point up here, and we're done. We have inserted a new item at the beginning of the linked list. Took like maybe 3 or 4 steps, right? So linked list insert is constant. Okay, so one of the most important things that you're going to talk about in your data structures class is how do I choose which one of these to use, right? And then you'll be studying a lot of other options too. But you know, if you're working on an application where there's going to be a lot of access and not very much inserting, then the array would be better, right? If you're working on an application where you're doing a ton of inserting things and not so much accessing things, then a linked list might be better. Okay. All right, so that was sort of a digression. I just wanted to give you some context there for why we would want to use this new technique. Oh, someone had mentioned about with an array, if I want to insert something into an array, sometimes I might have to actually create a whole new array because the array might be full, right? So that's another problem that you encounter with arrays that you do not encounter with linked lists, right? So if we've got an array and it's full and we want to insert something, we're going to have to create a whole new array that's bigger, copy everything from the old array into the new array, and then delete the old array. So that's very inefficient. Okay, let's write some code. Here's what we're going to work on. Not that, this. Okay, so what I have here is a client program that is going to use the class we're about to write. We're going to write a class called Simple List. You know, I could do an example that includes all the stuff we've learned about, you know, it could be a templated class and a few things like that, iterators and so on. But instead, I'm just going to write something and keep it as simple as I possibly can. So I call it Simple List. So let's just take a look at what we're going to need here. We're going to need a constructor. We're going to need a function named insert. And we're going to need a function named print. Right. And so what I'm going to do is I'm going to comment the rest of this out and just write enough of our class to get through these first few lines here. And as you can see, we'll be working on this for a while. Okay, so you can see that later on, we're going to write a size function. We're going to write a find function to find something in the linked list. We're going to write a del function to delete something in the linked list. And then we're going to talk about a copy constructor and the rest of the big three. Okay, so a lot of work to do, but for now we just need constructor, insert, and print. All right, so here's my class declaration. You'll see the constructor, you'll see the insert function, and you'll see the print function. In the private area of my class, what I've got is I'm declaring my node struct here, okay? And you can see that there are two data members there, right? We're going to have a data member to store the data and a data member to store a pointer to the next node in the linked list. You will notice that there's a little bit of circular going on here, right? But that's okay. C++ is specifically, has a rule that says that it's okay to do this. Inside my node struct, I'm using the word node, right? But that's okay. I'm just saying it's going to be a pointer to a node. And then here's my actual list data member. Any questions about what's going on here? So this node struct right here is the code that represents each of these boxes in the linked list. Okay, and I'm going to put this back to what it was originally. Because we're going to actually write the code to do that. Okay, any questions about the class declaration? Okay, let me just talk here. So this is another digression, okay? There's a lot of different ways that different programmers and textbook authors define this node. Some will insist that it should be a class and that the data member should be private. In that case, what you have to do is you have to have accessors and mutators for both of those data members. And then every time you're writing a member function, you have to, in the simple list class, you have to use those accessors, which makes things complicated and actually makes the code look really complicated. You can probably tell what my bias is here. And these are the struct node that I have here is declared in the private area of my class anyway. So the only functions that are going to have access to these, even though they are public data members of the node, the only functions that have access to them are the simple list member functions, which is perfectly safe. You also might find that an author might create a separate class named node that's not nested inside the simple list class. If they do that, they're going to have to either have mutators and accessors. I think that's actually what our textbook does, a separate class called node with accessors and mutators in it. Or you can have something called a friend class, right? So you can declare a separate class called node, and then inside the simple list class, you would make that class a friend of the simple list class. So lots of different options. I just wanted to throw that out there so that you won't be surprised if you see that not everyone does it the same way. I'm gonna just take a quick look here. I want to try to remember what we do, what our textbook does. I'm pretty sure it's a separate node class. Yeah, there's a separate list node class. And anyway, I guess I shouldn't take the time to do this right now. I'm seeing a struct called node. Yeah, okay. All right, so let's write the constructor. So when we first declare a simple list, what we want is we just want our data member list to be null pointer, right? So if I were to draw a picture of that, I would just put a line through this pointer variable here to indicate that it's pointing at null pointer, and that would be it, right? So next pointer on list dot get next and list dot next. That is one distinction. I'm not sure the syntax is 100% correct there, but that is basically the idea. Yes, and actually, when you want to, the mutator is even more complicated, right? Because you'd have to say list dot get a dot set next, and then give it a an argument. So, but yeah, basically that's the idea. Okay, sorry, I'm lost my, okay, so we're working on the constructor. Gonna need a file. And we're going to be # including simple list.h and using namespace std. Hold on here. Okay, and then I'm putting this all in a namespace. So namespace, I'll just harden list, we'll call it that. I think that's what I called it, right? Yes, okay. And I'm also going to need iostream here because I'm going to have a print function. Okay, so our constructor is just going to be list gets null pointer. That's it. Okay. Do we need that constructor, or is that just a convenience? So if we didn't have that constructor, then when we declare a simple list object in our client program, the list data member would be an uninitialized pointer. And so that could cause problems for us, right? So this is actually extremely important, even though it looks really trivial. It's very important that we get our list data member pointing at null pointer when a simple list object is declared. Okay, let's go ahead. I'm going to actually do print next because print is easier than insert. Actually, you know what? Let's not do that. That's going to be confusing. Let's do insert first. So when we insert something into the simple list class, it doesn't matter where we insert it. So we get to choose where to insert it. Will it be easier to insert things at the beginning of the list or at the end of the list? I guess I shouldn't say easier, I should say better. And also easier. So if we insert something at the beginning of the list, I already drew a picture of how that would work, right? We just create a new node, make the list point at that new node, and then make the next data member of the new node point to what used to be the first item in the list. Anybody want me to draw that picture again? That's how we would insert something at the beginning of the list. How would we insert something at the end of the list? Well, the first thing we would have to do is we would have to somehow get a pointer to the last item in the list, which would mean we'd have to start with a pointer pointing at the first item in the list, and then we'd have to keep moving down the list all the way until we got to the end of the list, and then we could insert something into the list at the end. Okay, so that would be a lot more complicated and also a lot less efficient, right? Every time we insert something at the end of a linked list, that's a very inefficient operation. Any questions about that? Why it's better to insert at the beginning of the list? Okay, so let's go through the code for insert. Sorry, my notes are totally messed up here. Okay, so it may look a little strange. In fact, let me just say that this doesn't actually make sense, right? Because you don't need to pass an int by reference. The only reason that I'm doing it this way is because I want to have enough flexibility in my code so that maybe later on I may change it so that that's an object instead of just a primitive type. So I'm going to pass it using const ampersand. Okay, so someone asked if it would be good if we saved the last node in the list as a member variable. The answer is yes, that is a very common technique. Often it's called a tail pointer. And in fact, in your assignment, you will be doing that. We aren't doing that. Yeah. But that's if for some reason you need to have access to the end of the list often, that's a good strategy. Okay, so insert. First, I'm going to create a new node. Okay, so the result of this code is that I now have a variable over here named new node. And it's pointing to a new node that has been allocated on the heap. I need a point. Okay, so that's a picture of the situation after this one line of code. Everyone okay with that? And it makes sense that we would need to create a new node, right? Because what we're doing here is we're going to insert a node into the linked list. So we need a new node. Okay, let's put the data in. Might as well get that taken care of. New node, arrow, data, gets insert me. Who needs me to explain the arrow notation here? I guess we haven't done much with that, right? I don't think you've used it in an assignment. So basically what I'm doing here is I'm saying, right, these two lines of code are equivalent. The arrow is just a cleaner way of saying it. So I call the arrow the dereference and then select operator, right? So we're saying start with new node. The star in front tells me to follow the arrow. And then the dot data says to give me the data part of what I find at the end of the arrow. And so when you see this arrow notation, until you become comfortable with it, you may just need to think it through and remember that it's actually a combination of dereferencing and then the dot operator. Okay. Any questions about what's going on that line? So that the result of that line of code is, it depends on what we're putting in there, but let's say that we're putting in the number 32. Okay. All right. Let's talk about what's next. So we want to make the next pointer of the new node point to the node that list is currently pointing at, right? We want to make this next pointer down here point up to what used to be the first item in the linked list. Notice we can't do it the other way, right? What we want is we want list to be pointing down here at the new node, right? But if we do that first, then we have no way of accessing what list used to be pointing at. So we have to make sure we do this in the right order. So make the next data member point to what list is pointing at. New node, arrow, next, right? So you'll see there's a pattern here, right? New node arrow data is how I initialize the data member of the newly created node. And now I'm initializing the next data member of the newly created node. And I want to make that point to the same thing that list is pointing at. So I just do a pointer assignment. And the result of that line of code is that now the next data member of that node points to the 47 node. Any questions on that step? All right, so now I just need to make list point to the new node. And the result of that line of code is list now points at the same thing that new node is pointing at. And so you can see now that we've got a new linked list with the 32 inserted at the beginning of the linked list. Any questions about that process? Okay, let me just point out here that I'm going to just clean this up a little bit here. So pretty straightforward function, right? Just 4 lines of code. And something that, so here's the number one important thing to remember when you are writing code for linked lists, okay? There are almost always going to be special cases that you need to make sure you are handling correctly. So often when you're writing a function for a linked list, you have to think, okay, does this work for an empty list? If the calling object was an empty simple list, does this work if there's only one item in the list? Does this work if I'm trying to insert at the end of the list? Does this work if I'm trying to insert at the beginning of the list? Does this work if I'm deleting but the item's not in the list? Really important to just think through every possible situation. And that's one of the main things that makes dealing with linked lists pretty tedious and easy, error prone, I guess I would say. Should it not delete new node at the end? Okay, so couple questions. Should we delete new node now? Anybody want to answer that question? Okay, what would that do? If I say delete new node right now, what does that do? Okay, so if I say delete new node, that means deallocate the memory that new node is pointing at, right? So that means this node right here is going to be deallocated. We definitely don't want that, right? So make sure you understand that, right? The delete operator does not get rid of the pointer, and we don't need anything to get rid of the pointer. The pointer is a local variable, so it's an automatic variable, right? Just like if we declared an int, we don't need to delete the int. Okay, so if anyone is still a little fuzzy on that, I really strongly suggest, I mean, this is gonna be like a million times more difficult if you're still a little fuzzy on delete. So you may wanna go back to the lesson on pointers and just review that. That may sound like putting extra time in, but my guess is that it'll actually save you time in the end if it helps you sort of understand a little better what's going on with delete. All right, so we're not going to delete new node. Right, so the next question was, doesn't this function assume that the next node exists? Well, let's see what, that's a great question. In fact, that's one of the questions you should be asking, okay? Because that's a special case, as I was just talking about. So let's see what happens if list is empty. So list is just pointing at null pointer, and we go through these 4 steps. Okay, I'm going to try to do this without drawing them, I think. So we're going to create a new node. That seems fine. We're going to put data, put the data in the data member of the new node. That's fine. We're going to make new node arrow next point to the same thing that list is pointing at, but list is pointing at null pointer. So that means we're setting new node arrow next to null pointer, which is what we want, right? Actually, you know what? I'm going to just draw a picture of that. Ignore this picture up here. Let's make a new picture that is going to illustrate what happens when list is empty. Just giving myself some more pointers. List is empty. That means we just put a line through the cell. That's how we draw null pointer. That's how we draw pointers that are pointing at null pointer. Okay. And so let's go through these steps again. Create the new node. Put the data in. So let's say we're inserting 32 into an empty list. Now we get to new node arrow next gets list. That's saying this new node. Oh, I should have drawn this. Sorry, I skipped a step. This is new node, and it's pointing at this, right? Okay, so when I say new node arrow data gets 32, that's new node arrow data gets 32. And then I say new node arrow next gets list, but list is null pointer, so that just makes new node arrow next equal to null pointer. And then I say list gets new node. So make list point to what new node is pointing at. And so we have a list with one item in it. And that's exactly what we wanted, right? Any questions about that process of how this works if list is an empty list? Okay. So I want to just get rid of all of this, I think. Delete's not in there. I guess I need to do it. Okay. This is part of where pen and paper comes necessary. Yes, definitely. This is where you're going to want to start drawing lots of pictures. Totally important. When you're working on your assignment, your labs for this, you're going to want to have a pen and a piece of paper handy. Or what, you know, a whiteboard or a pad that you can just draw with on it with using a stylus or whatever, right? But you get the idea. Okay, any questions about insert? I think this is still looking good here. So let's work on print. Okay, actually at this point, I'm gonna take a quick break. So I'm gonna pause recording and I'll be back in about 3 minutes. Okay, we're back. Can you hear me okay? All right. Okay, so how are we going to print? Here's the basic idea. First, let me just mention that normally a container class, which is what we're writing, right? We're writing a class that is going to contain items of some other type. Usually they don't provide a print function. That sort of makes, because you never know what sort of output device is being used by the client. So normally what you do is the client's responsible for printing and the class provides some way for the client to iterate over the entire container so that the client can actually do the printing, okay? We're gonna throw a print function in here just to make things easy for us to, so we can test things as we're going along here. All right, so we're gonna need, what we're gonna do, our strategy for printing a list, and let me, I should delete this new node variable, right? Because that was a local variable back when we were working on insert. But as it turns out, I'm gonna want to create a pointer that points to the first item in the list anyway. So I'm going, rather than delete this, I'm just going to call this cur pointer. Okay, so I'm going to create a pointer named cur pointer, and I'm going to make it point to the first item in the list. And then I'm going to have a loop where I print, and then I move cur pointer and make it point at the next node in the list. And then print that node, and then make cur pointer point to the next node in the list, and so on until I get to null pointer, right? So I'm going to say I need a pointer to a node. I'm going to call it cur pointer. And I'm going to start it off being equal to, or pointing to the same thing that list points to, right? Any questions about that line of code? Right? And then I'm going to say, as long as cur pointer is not equal to null pointer, I'm going to print what cur pointer is pointing at. So cur pointer, arrow, data. And then I'm going to move cur pointer so that it is pointing at the next node. Whoa, the next node, right? I want to move it so it's pointing up here, which is the next node. In other words, I want to make cur pointer point to the same thing that cur pointer arrow next is currently pointing to. Type of cur pointer. Thank you. Right, let me say that again. I want to make cur pointer point at the same thing that cur pointer arrow next is pointing at. So that's make cur pointer point to the same thing that cur pointer arrow next is pointing at. That makes sense what this does? So I'm gonna, that just means, all right, make this point here. All right. So then I go back up to the top of my loop, cur pointer is still not null pointer, so print the 47, and then move this to the next node. And go back up to the top of the loop, cur pointer is still not equal to null pointer, so move it, so print out the 19, and then move cur pointer to the next node. Cur pointer still not null pointer, so print out the 62, and then make cur pointer point to the same thing that cur pointer arrow next is pointing at. But cur pointer arrow next is null pointer, so at this point, cur pointer just becomes null pointer. Right? Any questions about how print works? I guess I should do this, and then when I'm done, I will. Okay, any questions about any of the code you see here? What is list again? List, well, in the picture, list is here. List is the private data member of my class, right? So it's a pointer to a node. Everything I want to do with anything in this linked list, I'm going to have to start with what list is pointing at. All right, so let's see how we're doing here. I'm not at all confident that this is going to work the first time, but we'll see how we did. Simple list client.cpp. And then, oh yeah, simple list.cpp. Print is not massive. Okay, so on my print function, I forgot my const, I'm assuming, yeah. Okay, so let's look at my client program so we know what to expect when we actually run this thing now. Basically, I am asking the user to enter a bunch of numbers, and I'm just putting them in the list and then printing them out, okay? So enter a number, negative to quit, so I'll go 5, 6, 7, 8, 9. Okay? Hopefully it makes sense that they came out in reverse order, right? Because every time we insert something, we are inserting it at the front of the list. So we first put the 5 in, and then we put the 6 in front of the 5, and then we put the 7 in front of the 6. So when we're done, our list looks like 9, 8, 7, 6, 5. Any questions about what we've got so far? Okay. Let's see if we can do one more. Well, at least one more. So yeah, the next one in our client is size, and that's pretty trivial. So maybe we'll try to get on to find also, but let's see how this goes. Okay, so what I'm going to do now is I'm going to write a size function. It's not at all, sorry, I just realized that this isn't going to be as trivial as I was thinking it was. So we'll probably just wrap it up with this. But so it's not at all a bad idea to actually have a data member in your class that keeps track of how many items are in the list, right? That way, I mean, since I don't have that, and I'm gonna keep it that way, if nothing else, just so that we can have some more fun with this. But what I'm gonna have to do to figure out the size of the list is I'm gonna have to kind of do like what I did when I was printing, right? Move a pointer down the list, but instead of printing each node, I'm just going to count each node. So obviously that's less efficient than if I had a data member called, say, num items or something that I just kept updating. I will argue, and you know, the bottom line is that's probably a good idea. I could make a case though that it's not necessarily more efficient, because if I have a num items data member, that means that every time I insert something into the list or delete something from the list, I have to update it. So that's inefficient. If I'm in a situation where I never ask or rarely ask for the size of the linked list, but I am constantly inserting and deleting things, it might actually be less efficient to have a num items data member in there. So anyway, just had to babble for a minute about that. We are not going to use a num items data member. Not necessarily because we think that's better. That's just what we're going to do. All right, so let me add my size member function to my class declaration. And actually what I'm going to do there is I'm going to create a size type, which you've seen before, right? And then my size member function returns a value of type size type. Everyone okay so far? I'm not sure why we can say T, we aren't using a template class. Size T actually has nothing to do with whether we're using a template class or not. I mean, I guess when I explained size type, one of the motivations I said was, well, this is how the standard template library does things, but that's not because they're templated classes. Okay, yeah, it is too much of a tangent. It's super not critical. So don't worry too much about it. My guess is, yeah, if I had to do it over again, I might just skip size type altogether and just use int because that's how important or how not important it is. But we're going down this path now, so I'm going to stick with it. Yeah. And, you know, did my best to explain the motivation for it in the lesson 19, where there's a whole section of the lesson on size type. So you can give that a try too, and see if that helps. Okay, so for size, as I mentioned, basically what we're going to have to do is we're going to create a curve pointer. And we're going to move it down the list exactly the same way we did when we were printing. But inside this while loop, like if you were to look at the print function, it's going to look exactly like this, but instead of printing each node, we're just going to say count plus plus each time through the loop, right? So node star curve pointer gets list. We're going to need a count. And then we're going to have our while loop. And then instead of cout, we're just going to say count plus plus, and then move curve pointer down to the next node. And then at the end, we're just going to return. Okay. I mean, the one I kind of like that we're doing size type, if nothing else, just because it requires us to do a little more interesting things like recognizing that we're going to need simple list : in front here, but not here, because by the time we get here, we're inside the scope of the class. Well, I do need, I'm missing simple list here. Any questions about any of the syntax going on here? All right, let's give it a whirl. Oh boy, what did I do? H, did I forget? Yeah, I don't have, let's try that. Size type. Size type. So simplest.h line 13. Oh, oops. Try that. There we go. 1, 2, 3, 4, 5, 6, 7. There are 7 items. Which line? So STD is defined inside the IOString class, among other places. But if I didn't # include anything at all, then I would never have the identifier STD. The other thing is size T actually, I think, is defined inside CSTDLIB. So technically I should be doing this also, but I think on most systems it just gets automatically included. But in any case, I should be including that. Okay, so there's your, for most of you anyway, I assume that's your first look at linked lists. Hopefully that makes sense. Basically, what we're going to be doing from now on is just, I'm going to add a couple more functions to the simple list class, and then we might work on a bit of a more complex linked list class that would more closely simulate what's going on in the standard template library forward list class. this is one of the reasons this is super simple is that I'm only just inserting things at the beginning of the list. That's really not all that useful most of the time. Most of the time, you're going to want to have a little more control over where you are inserting things. But anyway, so we're a little early, but I don't want to start on the next function because it's going to take way more than 5 minutes. Should we be including any more of these? Yes. And typically when you're using if you're not sure where something is defined, you may have to go to c++.com to find out what library it is defined in. But that certainly would be best practice. I have to admit, it's not something that I am very good at checking to make sure you're doing. But yes, that would be the right thing to do. Any other questions before we call it a day? All right, so I will see you on Wednesday.